Hello guys, we are back with part 2 of Acid Base 103, and I'm going to scoop this up a little bit. So I just want to draw your attention to right here, which is where we're starting. And this is a lesson on calculating the pH from initial concentrations of HX, and this is for a weak acid. So we want to remember or know that pH is found using equilibrium concentration of H3O+. You negative log the H3O+ concentration, you get the pH. And this is for weak acids only. Because strong acids, there's no equilibrium. Therefore, the concentration of the acid is equal to the concentration of the H3O+ for strong acids. Okay, so for weak acids, you use the Ka value and an ice table to find the equilibrium concentration of the hydronium, and then you negative log this value. So I'm just going to walk through an example, and so here we go. Here's the example, and we are going to calculate the pH of a solution that is, we'll say 7.5 times 10 to the minus 5 molar in acetic acid. So there's the prompt, and I'm going to switch pages here. You can pause that as necessary. Okay, so the first thing you want to do is make your paper straight, because that's very important. So the first thing you want to do is write the equilibrium. Reaction for the acid that will affect pH, or affect the concentration of the hydronium ion, which is therefore pH. Okay, so you look on here, and you would find acetic acid is right here, right at the top, HCH3COO. And that will be aqueous plus water, liquid, and that'll be in equilibrium with this minus this first hydrogen. So you'll have CH3COO -1, which you may recognize as the acetate ion, and then we'll have hydronium. Okay, so down the left-hand side of your paper, you are going to write ICE, I for initial, C for change, E for equilibrium. And what we want to know is the pH. So we're interested in the concentration of the hydronium ion at equilibrium down here. Okay, and we are given in the problem, put that back up there, that 7.5 times 10 to the minus 5 molar in acetic acid. And just to make a note, anytime you're given a concentration, you make an assumption that that concentration is an initial concentration unless you're told otherwise. So this concentration that's given, the 7.5 times 10 to the minus 5, goes right here. Okay, the water, we're going to write a line under it because it's a liquid, so I call that the I don't care line, or the we don't care line, because it's a liquid, so it's not involved in any equilibrium. These guys initially, so before an equilibrium is established, these guys are going to be 0. And now we don't know how much of the acetic acid is going to ionize into CH3, COO, and hydronium. So we're gonna let X equal the change. Okay, so we're gonna have a loss of X here. We're gonna have a gain of X here. A gain of X here.
Go potty.
Emmett, just go. You don't need to say it on video. Close your door. Okay. And so at equilibrium, these guys' concentration could be represented with X. And then we'll have 7.5 times 10 to the negative 5 minus X. Okay, so our next step is we are going to estimate X out of the equilibrium concentration of HX, whatever the acid is. And the reason that we can do that is because the Ka is small. Therefore, the change in this acid concentration is going to be very small as well. So Ka is small, therefore X is small. So we can say, therefore, 7.5 times 10 to the minus 5 minus X is approximately equal to 7.5 times 10 to the minus 5. Those are approximately equal to signs. Okay, so the way that I usually explain this is that X is negligible. X's value is negligible compared to the initial concentration. And you could think of it like if I was talking about the mass of the Earth and I lost, like one flea like jumped off the Earth into space, the mass of the Earth would be relatively the same because the mass of the Earth is so big. If it loses a flea, then because the flea is so small compared to the Earth, it's negligible. So the 7.5 times 10 to the minus 5 would be the mass of the Earth, and the X is the flea. So we can say this guy doesn't make a difference. Okay, so we let X equal the change. We estimated X out, and then we're going to write the Ka expression. And solve for X using Ka's value. All right, so we know Ka is going to be equal to the acetate ion concentration times the hydronium ion concentration over the initial acetic acid concentration, CH3COO. Oh, sorry, the equilibrium concentration of the acetic acid. Okay, so we've let X represent both of these, so we're going to substitute here like that. And so we get X times X, and then we would have this guy would be substituted here, but remember that we're estimating X out. So the 7.5 times 10 to the minus 5 minus X is approximately equal to 7.5 times 10 to the minus 5. And that is going to be equal to the Ka for acetic acid, which is 1.8 times 10 to the minus 5. And we would find that information right here for acetic acid. Okay, so we end up with X squared over the initial concentration is equal to the Ka, 1.8 times 10 to the minus 5. So I'm going to use my calculator. And say 1.8 second E negative 5 times 7.5 second E negative 5. And then I'll square root that. Then I get X equals 3.7 times 10 to the minus 5 molar I'm sorry, they're doing construction on my house right now. Almost in. So this is the hydronium concentration. That is ridiculously loud. Okay, so the negative log. That's going to give us pH. So 14 minus 4.4 is going to give us the pOH. 9.6. Okay. Sorry about the noise at the end. Bye.